Welcome to Brain Vision.
This is chapter 27, problem number 56. We have a cyclotron and the maximum radius of the circular trajectory of a particle is given to us as on an axis 0.44 meters, and the magnetic field inside the cyclotron is given to us as 0.85 teslas. In part A, we are trying to calculate a maximum kinetic energy of a proton that is accelerated by a cyclotron. In order to figure that out, we need to first calculate the maximum speed that the proton can have. From there, we can go to kinetic energy, the maximum energy that this proton can have using this equation. So how we're going to get to the maximum speed is from the magnetic force. QVB is going to be generating the centripetal force, which is equal to mv squared over r for this given radius. These are going to cancel out. So if we're isolating the max, then we're doing Q times V times R over S. Now plugging in the values, 1.6 times 10 to the power negative 19 coulombs times 0.85 Tesla, 0.4 meters divided by 1.67 times 10 to the power negative 27 kilogram per proton. We find the maximum speed to be 3.257 times 10 to the power of 7 meters per second. Now calculating the kinetic energy, then we're going to 1/2 mv max squared. This is the maximum energy this proton can have. 1/2 1.67 times 10 to the power negative 27 kilograms times 3.257 times 10 to the power 7 meters per second squared. Then we find the maximum energy to be, well, we're asked in both units, right? First, well, this would be 8.9 times 10 to the power negative 13 joules. So if we divide this by 1.6 times 10 to the power negative 19, then we can find the kinetic energy, maximum kinetic energy in terms of electron volts. It would be equal to 5.6 times 10 to the power 6 electron volts. So either this answer in joules, or we divide it by the charge of a proton, and we find it in terms of the electron volts. Now, in part B, we're asked to calculate the period of this rotation. It would be the circumference over the speed, right? So 2 times 3.14 times 0.4 meters divided by 3.257 times 10 to the power 7 meters per second. That is going to give us the period of this rotation, 7.771 times 10 to the power negative 8 seconds. In part C, now in part C we have a different magnetic field that we're trying to actually calculate for. The magnetic field corresponds to the twice of the kinetic energy that we calculated in part A. So in part A, remember what we did? Well, first we did QVB equals mv squared over r. So from here, B would be QBr over mass. And then we said the kinetic energy then is going to be equal to 1/2 m square of this term, right? Q squared, B squared, R squared over M squared. So what M's are going to cancel out? 1/2 Q squared, B squared, R squared over M. That's what we exactly did, right? So now from this equation, we're relating the kinetic energy to the magnitude of the magnetic field. If we isolate B out of the equation, what would we get? We would get 2 times the kinetic energy times the mass divided by Q squared R squared and the square root of everything, right? For a given kinetic energy. Now, what we have is now we're given a different magnetic field. Let's call it B prime. And the condition is that we're doubling this kinetic energy term. So it's going to be 2 times of the kinetic energy times m over q squared r squared. So then if we write this new magnetic field in terms of the old magnetic field, what can we do? Square root of 2 times square root of 2 ke m divided by q squared r squared. So then this term would give us the initial b, right? So then square root of 2 times the initial b gives us the final b. So then from here, our b prime would be equal to square root times 0.85 Tesla. It would give us 1.2 Tesla. Now, part D. In part D, we're trying to calculate the maximum energy that alpha particles this time, not a proton, alpha particles can have by being accelerated by the cyclotron. This is going to be just like part A, right? Like part A, we're going to borrow the equations from part A. We had solved for V max. We're going to follow the same routine. Q, B, R max divided by the mass. 3.2 times 10 to the power negative 19 coulombs would be the charge. 0.85 Tesla is the magnitude of the magnetic field. The radius is 0.4 meters. The mass for the alpha particle is 6.64 times 10 to the power negative 27 kilograms, almost like 4 times the charge of a proton. So then from here, we calculate the V max for an alpha particle to be 1.64 times 10 to the power 7 meters per second. Then we're going to plug it in the kinetic energy equation. What we get is 1/2 6.65 times 10 to the power negative 27 kilograms, 1.64 times 10 to the power 7 meters per second squared. That would be equal to 8.9 times 10 to the power negative 13 joules again. Again, if you want to convert this to electron volts, we already calculated in part B. Going back, excuse me, we had calculated it in part A. My apologies. So then we had done the conversion. It was 5.6 times 10 to the power 6 electron volts. So the question continues as, oh, okay, now, well, we find the kinetic energies for an alpha particle and the proton to be pretty much the same, right? Because this is the same answer as part A. And the reason for that is basically, let's go back to the kinetic energy term. The kinetic energy term is 1/2 q squared b squared r squared over m, right? We had derived this equation. Now, for an alpha particle, basically the mass is like 4 times greater, right? But q is twice. So then when we take the square of it, still roughly we're basically multiplying the kinetic energy by 4, but dividing it by 4, so we're getting pretty much the same kinetic energy that we have for a proton for the kinetic energy of the alpha particle.